Good afternoon to you all. Today I'm going to present you some talk about J2ME security vulnerabilities. I will present you the results of my work that I took during the last 7 months. So let me introduce myself a little bit more, who I work for and what team I work for. So I work in Poznań Supercomputing and Networking Center, which is a leading research network and supercomputing facility in Poland. We are the operator of the Metropolitan Area Network. We are also the operator of the Polish National Academic Network, the so-called Pioneer. We lead many research projects funded by the Polish State Committee for Scientific Research as well as European Community. And we are also the Center of Excellence for Greece. But I'm primarily the member of the security team of PSNC. And as a security team of PSNC, I take part in a lot of tasks dedicated to the security of the Pioneer network itself, PSNC's supercomputing resources. I also take part in real-life large-scale penetration tests that we conduct in our company. And these are the tests, security audits of software performed for third parties primarily, and this includes both commercial as well as educational ones. So we also participate as security consultants in research projects funded by Polish State Committee for Scientific Research, European Community, as well as IT vendors. I think that our team, myself, has quite extensive knowledge of attack methodologies and techniques. And what's the last news is that we also try to perform continuous security vulnerabilities research. So these are some of the introduction words about myself, my company, the team I work for. And what's the goal of this presentation? I will be talking about some new threats here today. And my goal is, I believe that practical security in general is not only about the knowledge about protection, it's also the knowledge about the threats. So regardless of the very solid security design that Java language has, there has been many attacks performed against JVM in the past. This includes both Sun microsystems, virtual machine, as well as Microsoft one. So far, no problems have been reported in KeyVM, the virtual machine used in mobile Java technology. This might indicate that the whole security of this KeyVM and mobile Java has been taken as is. And I also believe that showing the real threat of a given technology is one of the ways to build proper awareness among the users of a given technology. It also usually motivates vendors of a given technology to build more secure systems. Okay. So what J2ME is? This is a technology that has been developed primarily as a technology for execution of Java application on mobile devices which are constrained, have limited resources with regard to memory, CPU power, etc. And currently, J2ME considers mainly mobile phones, PDAs, but also TV set-top boxes, in-vehicle telemetry, etc. J2ME is the younger sister of the Java 2 second edition. So it has all of the characteristics of the Java language itself. So when you look at this technology roadmap of Java, you can see where actually J2ME is placed. So we have J2EE platform, which is primarily used on servers, enterprise computers. We have J2 standard edition, which is primarily used on servers and desktop computers. And this is the Java platform that is, for example, used on web browsers. Here we have Java technology that is used on smart cards, the so-called Java card. And between J2 standard edition and Java card, we have a Java micro edition platform, which is primarily used on high PDAs, TV set-top boxes, mobile phones, and PDAs. So let me give you a few concepts about Java mobile edition before I go with the details of vulnerability, security architecture, etc. So first, the key concept in J2ME is configuration profile. Configuration is a set of hardware functionality which is usually made available to applications through a given JVM. Currently, J2ME defines two basic configurations, and these are CDC and CLDC. And profile profile, this is the API exposed by a given J2ME implementation. And currently there are 4 APIs that are actually defined. This includes MIDP, Foundation, Basis, and Personal. Out of these 4, MIDP is the most popular, the most common. So as for SDC and CLDC, which stand for Connected Device Configuration and Connected Limited Device Configuration, these are actually specifications for the basic Java virtual machines that a given J2ME device must support. So CDC and CLDC, these are not actually the APIs. These are just specifications of the runtime environment. So at the heart of CDC and CLDC, there is always a given Java virtual machine. In the case of J2ME, this is KVM. And as for MIDP, which stands for Mobile Information Device Profile, this is the API which is actually exposed by small mobile devices. And this API actually concerns those devices with graphical displays. And as I mentioned, this is the most widely supported API. So let me tell you a bit about Key Virtual Machine. This is a key feature of J2ME technology, and this is highly portable Java virtual machine. It has been designed from ground up for small constrained devices with limited amount of memory or limited CPU power, with devices that are network connected. So KVM is suitable for 1632-bit RISC-V microprocessors. It is primarily run on ARM microprocessors, as far as I know. And the total memory budget of no more than a few hundred kilobytes. So in a common scenario, KVM takes about 128 to 256 kilobytes, out of which about 40 to 80 kilobytes are needed for the virtual machine itself or its runtime engine, runtime environment, and the rest is reserved for configuration and profile classes. So before I start talking about specific attacks against KVM, I think that I need to tell you a bit about security model that is used on mobile Java. So this security model is primarily defined at 2 levels. The first level is the lower one, and at this level, it is ensured that Java applications which run in the virtual machine follow semantics of a Java programming language. So at this level, Java virtual machine makes sure that no ill-formed or maliciously encoded class file doesn't crash in other way or harm the host device. So in standard Java virtual machine, the security at this level is usually implemented and guaranteed by the so-called bytecode or class file verifier. And we also have some higher level of security, and this is application level security. And CLDC application level security is usually accomplished by using the so-called metaphor of closed sandbox. So actually, applications that run in J2ME environment, they run in a very closed environment. And in this environment, the applications can access only those libraries and device resources that are predefined and specified by configuration profiles and other classes supported by given device. So in normal way, Java application cannot simply escape the sandbox defined by these configuration profiles and other classes. They cannot access any other libraries or resources on a given device. So the sandbox ensures that any malicious or possibly erroneous application cannot gain higher privileges on a given device. So what's important for the sandbox model is that it requires that through downloading, installation, or management of Java applications, there is no way to bypass the standard class loading mechanism of the virtual machine. This is very important because if you are able to bypass class loading mechanism, you could, for example, inject or spoof some system classes. Additionally, a closed predefined set of Java APIs must be available to the application programmer, and it must be specified explicitly. There couldn't be a way to use some other classes, some other APIs defined by application programmers, so that through this API there could be a possibility to access some sensitive resources of a given device. Additionally, sandbox model requires also that a set of native functions that are actually available for the Java application run on a mobile device, this set of functions must be closed, so there cannot be any way to access any other native functions of the host operating system, for example. Because if there would be such a way, Java applications might, for example, communicate with some other processes residing on the phone, or to access some functionality of the device that could simply harm this device. So there are also some additional security restrictions that they are not so tied with the whole sandbox model, but they are much more tied with the so-called CLDC implementation, the Java virtual machine itself. And these security restrictions say about what a given application cannot do. So first of all, given application cannot override, modify, or add any classes to the protected system packages. So protected system packages usually make part of the core Java virtual machine environment, so they cannot be changed or modified in any way. Because if there would be such a possibility, this might influence the security of the whole Java virtual machine and Java environment. Application cannot also manipulate the classifier lookup order in any way, because if they could manipulate this classifier lookup order, they could, for example, inject some user-defined classes before the actual system classes. And by default, Java applications can load application classes only from its own Java archive file. This last restriction simply says that a given Java application can run in its own closed environment and cannot just interfere with any other Java applications installed on a given device, for example. So there are two primary levels that are responsible for the security of mobile Java, but the Java language itself has some built-in security features that makes it very from design, it makes it a very secure language for mobile code. So first of all, what's very important to say is that security of data in Java language is imposed at the language level. So every piece of data must have a given access scope specific identifier associated with it. And these access scope identifiers can be associated with classes, field variables, and methods. These access scope identifiers simply tell whether a given piece of data, field, methods, or class can be actually accessed and by who, what class, etc. Java also enforces memory safety, the so-called memory safety. This enforcement is done by virtual machine itself, and this is done simply because security of mobile code in Java, the approach that has been taken in Java to mobile code security, is primarily based on the assumption that secure code is all about secure memory accesses. So, and now you can see a few of the security features of the Java language that are primarily responsible for implementing the type safety, memory safety of the Java. So we have garbage collection mechanisms in Java. Memory can be implicitly allocated, but it cannot be implicitly freed by Java application. So it's up to garbage collector to collect unused memory chunks and compact the memory heap so that it can be used for Java application during new malloc operations. When it comes to type safety, there is strict type checking of instructional parents done in Java, and there is no pointer arithmetic. When it comes to type safety, it's up to bytecode verifier to ensure that Java is actually a type-safe language and that Java adheres to the JVM specification. It's very important, and I think that it's at the core of the Java security fundamentals. So there are also many runtime checks, and these are performed usually when it comes to array accesses, cast operations, and when it comes to string literal representation, they are represented as UTF-8 strings. This in some way can prevent naturally from the so-called buffer overflow attacks, etc. Because this representation contains information about the length of the string embedded in the data representation itself. So what are the differences from the standard Java 2nd edition? There are many features that have been simply removed because of the security concerns. They have been also removed because of the limited resources and the limited availability. This especially concerns the amount of memory available for J2ME applications and the whole environment. So Java native interface has been removed, user-defined class loaders have been removed. This second feature has been removed primarily because there were many problems in the past with regard to class loaders. We don't have reflection, thread groups, daemon threads, finalization with references, and errors as well. Some of them were removed because of security concerns, some of them because of the limited amount of memory available. So now I need to introduce you to the bytecode verifier, and before I start talking about the flaws, because the flaws I will be presenting to you are tightly connected with the bytecode verifier itself. So bytecode verifier is part of the Java virtual machine, which is primarily responsible for verifying that the items stored in class files do not contain illegal instructions, that the instructions are not executed in a legal way, or that the class files do not contain references to invalid memory locations, and this especially concerns some memory areas that are, for example, outside of the Java object's memory, or the object heap. And bytecode verifier ensures that Java code is type safe. Yeah? This is this component of Java virtual machine that is primarily responsible for maintaining Java language type safety. And it verifies whether the actual Java bytecode adheres to the semantics of the Java programming language defined in Java virtual machine specification. So, speaking about the checks that bytecode verifier does, so it primarily checks whether the code doesn't forge any pointers. Yeah? Everything must be under control of the Java runtime. Programmers cannot forge pointers, for example. Bytecode verifier checks whether class file format is okay, whether the code doesn't violate any access privileges, whether the class definition is correct, for example, whether this is checked just in order to make sure that there are no buffer overruns, etc. Also, there are some checks that make sure that no stack overflows occur, no stack underflows occur, that all uses and stores of local variables or stack items are valid. All parameters of bytecode instructions are checked, and all accesses to object fields are also checked when it comes to the public, private, and protected access code identifiers. So the classifier verification, this is the process during which the bytecode verifier checks all of these constraints presented before. However, the existing J2 2nd edition bytecode verifier defined in the specification didn't suit very well this new environment, the environment in which the environment of small resource constrained devices. And this was primarily caused by the fact that it took about 50 kilobytes of binary code space and at least 30 to 100 kilobytes of dynamic RAM at runtime. CPU power that was needed to perform the whole iterative data flow was also exceeding the available CPU resources. This is why in J2ME, another approach has been undertaken. And in this new approach, the whole verification process has been split into two phases. So we have a phase which is done off device, yeah, the so-called pre-verification phase. And during this phase, the standard Java 2 2nd edition bytecode verifier is used. And in this phase, bytecodes and class files are simply pre-verified, and additionally, a special stack map attribute is added to class files to help perform the second phase verification, which is done at runtime. And the second phase verification is done at runtime, and it uses the stack maps produced in the first phase. So while talking about stack maps, here you have an example code, just some method that just returns a string objects, and it calls the shipper class toString method. What's important when it comes to stack map attributes? Every stack map attribute has a given number of entries. In this case, we have 2 entries. Every entry is associated with a given bytecode offset. And every entry contains detailed information about the number of local variables, types of local variables, number of stack items, the height of stack, as well as the types of stack items. So, in other words, stack map attributes describes the state of stack and local variables for code allocations that can be primarily used across different execution paths. That's not true for every case, but they, in this case, they are associated with 11 and 13 bytecode offsets. Yeah, this is primarily caused by the fact that it is possible to make a jump from one bytecode location to the other one bytecode location. And because the places where the state information with regard to Java bytecode merge, these places are the most prone or vulnerable to any, type manipulation or attack. And this is why stack map attributes are primarily associated with the targets of any jumps. So, talking about bytecode verification, I should also mention that the whole algorithm that bytecode verifier does is primarily based upon data flow analysis. And this data flow analysis is done by modeling the execution of every single bytecode instruction. So every instruction is inspected by bytecode verifier, and every execution path that can be taken in a given bytecode method is actually also inspected. This is especially important because if you want to make sure that a given Java bytecode is safe, you must be sure that there isn't any code path in a given method that could, for example, take some malicious or some wrong actions that do not adhere to the Java language specification semantics. So you must make sure that the type safety across any given path in a Java bytecode is maintained. So for each instruction, information about the number of local variables, stack height, the types, which are contained in registers and stack, this state information must be maintained for every single instruction during the bytecode verification process in order to make sure that a given code is type safe. So what's interesting about bytecode verification algorithm is its approach, because regardless of the fact whether there are some branches forward or backward, the bytecode verification algorithm always runs literally across the code. So it's a bit different in this way how it operates in the case of standard J2SE bytecode verifier. So the code is, in the case of J2ME verification algorithm, it is verified instruction after instruction. So linearly, the code is looked up, and every instruction parents and their types is checked. State information. If there are some, incompatibilities, that obviously indicates that the code might not be safe. Yeah, and this is the actual idea that's behind this verification algorithm. So obviously, I have no time to go deeply into the whole verification process, but you can have a look at the CLDC specification, the supplement to this specification, CLDC bytecode type checker specification, which talks about the whole algorithm, the way the bytecode verification is performed in J2ME in a very detail. So before approaching J2ME, I've been involved in finding some other vulnerabilities in Java virtual machine implementation, and this considered Sun virtual machine as well as Microsoft One. When I first approached J2ME, I just made a list of some potentially weak components, which security researcher always tries to have some weak points, and then he tries to investigate these weak points whether they're actually properly designed or properly implemented. And this is the list of components that I've made while approaching the J2ME after making the whole entry work, which is related to getting familiar with this technology. So definitely bytecode verifier. This is my favorite topic. I've been involved in analyzing, researching the work of bytecode verifier for a couple of years now, and this is actually one of the key components responsible for Java security. There's also KVM runtime, the so-called execution engine. This is also the place where some potential vulnerabilities might exist. This specifically concerns the invocation of virtual methods. Yeah? So there might be some flaws in the way just-in-time compilation is performed. There were flaws in just-in-time compilation in the past, for example, semantic JIT compiler flaw from 202. There are also some weak points that might be related in the way some core CLDC and MIDP classes were implemented, and what's primarily important, the way in which some vendor-specific classes are implemented, because these classes are not usually published. The implementation isn't known, the API isn't known. This is the thing that is usually known to the vendor itself. So vendors usually do not apply to this stuff with regard to security in a way that they should. So there are also some potential weak points related to native methods implementation, because although Java is a type-safe language, everything is under control of bytecode verifier and Java virtual machine during the bytecode execution. There is some interaction between the Java code and the native code, and this primarily includes calling some native functions, the functionality of some underlying operating system itself. So this is the place where, for example, buffer overruns could be placed and could be, for example, spotted and exploited, etc. So this is the next slide presents the first vulnerability that I found in KVM implementation, and actually concerns the bytecode verifier. The problem here is that having, excuse me, just had some problems. The problem with the first flaw is that, as I said, every bytecode location to which an execution is directed to, it must be, with such a location, there must be associated a proper stack map entry. The first two slides. Here, okay, thank you. And as I said, with every target of a jump, like here, we have some constructor, and in the body of this constructor, we have one instruction. This instruction simply diverts execution to the location specified by in the instruction itself, and in this case, we have 66 locations. So, according to J2ME specification, CLDC specification, and the way J2ME operates and verifies codes, we need to have proper stack map attribute that is associated with the target of this go-to instruction. The problem with KVM implementation here is that although bytecode verifier that the go-to instruction has a stack map entry associated with it, it simply doesn't verify whether the target of the go-to instruction is within the limits of a given method. So here we actually are able to simply jump off a given code to some arbitrary locations. This includes jumping forward or backward of a given code. So this is what's about the first bytecode verifier flaw. And there's also the other flaw, which is also related to the instruction that changes execution flows in some way. The second vulnerability is connected with the go to white bytecode. And the problem here is that although in this case bytecode verifier checks whether the target of the go to instruction is legitimate, yeah, it doesn't actually, it does some very weird operation before this check, because it simply casts the offset here specified in the go to white instruction from 32 bits, because it's for go to white instruction it's 32 bits long, to 16 bits, because in stack map entries this bytecode offset is actually 16 bits long. So the problem here is that the cast from 32 bits is made to 16 bits, And after casting this value to 16 bits, we yield offset 0. And of course, 0 offset is legitimate according to bytecode verifier. But bytecode verifier should follow completely different execution path. And this is the reason why we have a problem here. Because again, we are able to jump off the code of a given method to some arbitrary locations. And this shouldn't be done because every execution path should be verified by bytecode verifier, and this is not the case here. So, what's in the result we can gain having these flaws? First of all, we are able to jump to some arbitrary bytecode locations outside of the current method. Yeah, this can be done. Secondly, since bytecode verifier operates on a single method basis, it just takes the given methods and checks whether it is type safe. Yeah, bytecode verifier isn't actually able to catch this situation that there is any jump out of a given code or of a given method. It isn't simply able to detect such a situation. And in the result, we are able to simply escape the KVM sandbox, and we are able to execute some Java bytecodes that reside on some completely other path, on the path that hasn't been verified by the bytecode verifier. So this is just the beginning of the whole range of attack possibilities that can be performed against. So the fact that you have to load your own Java applet or whatever onto the device. Yes, exactly. So what I should maybe indicate here is that the exploitation of every of these flows requires that users download malicious applets onto their phone. This is the first step, and secondly, they must run it. Yeah, these are not remote vulnerabilities in the way that it is possible for. I am not aware of any way to, for example, remotely upload some Java midlet, because they are called midlets, onto the phone. We can talk about, for example, while IP. Yeah, you can browse some while IP pages, and there might be some midlet embedded on them. But usually the user is warned about such a midlet, and he's asked for whether such a midlet can be downloaded onto the phone, or whether he wants to run it. Yeah.
How about blue snuffing?
I was thinking about whether it could be possible to actually inject some Java application into the phone through blue snuffing. However, and Bluetooth flaws reported about by Mark Lorry a year and a half ago, but I haven't actually verified that. So I don't know. So coming back to the exploitation issues of the flaws, this is the beginning, because at this point we are able to just start attacking Java. Having a flaw itself and bytecode verifier, this is a far away from a flaw to performing a given malicious actions. There is a far way. Yeah, it took me about 4 months of very detailed reverse engineering of the phone from having a given flaw to actually do something malicious on the phone. So it's not easy. It's not so easy. So anyway, but this is the beginning, and this actually can be done, and I want to show you that this can be done in this presentation. So, I'm sorry, don't know why it just skips through so many slides. Here, okay. So, as I said, through the 2 KVM flaws, it's possible to jump to some arbitrary code locations, to some locations that are specifically outside of a given method, Here you have some exploitation method that, for example, does a jump to some backward jump to some arbitrary location. And in order to properly exploit such a condition, we must have a proper class file layout in memory. So jumping forward will actually put the execution flow in some code location that is completely under our control. Only upon having such a proper memory layout, we can actually do something that is completely deterministic. And it's very important, because it's not exploitation is about having some deterministic results. It's not about proving that you can jump somewhere and obtain some illegal bytecode exception or phone restaurant. Yeah. So this can be done by having proper class file layout. I was usually doing this by jumping forward to some method that was quite long. It usually was filled up with 32,000 of return instructions. I was jumping in the middle of these instructions, and by doing so, I was able to, for example, perform some arbitrary cast operation and KVM. And I was simply using the way the KVM was allocating memory, and from my experience on my Nokia phone, I know that the memory has been allocated from top of the heap to its down, from higher to lower memory addresses. Okay, let's try. Oh, yeah, it works. So, what's important when it comes to exploitation reliability? I have to admit that this was the most difficult work that I have been ever performing when it comes to security research. One of the most obstacles was caused by the garbage collector behavior, because in Java, every malloc operation is under complete control of the Java virtual machine runtime and garbage collector. Every dynamic Java object has a garbage collector header, and this header stands whether this is a method table, whether this is a field table, whether this is an object instance, etc. So when it comes to, for example, when Java runtime is running out of memory, garbage collector starts its work, and garbage collector simply compacts the memory, the dynamic heap memory, in such a way so it just rewrites memory regions in such a way so the whole region is compacted in one solid block. And how does it actually influence the whole exploitation reliability? This is quite obvious because you don't have a situation when you have some memory block in which you have your code where you can jump, etc. You have a situation where you have some dynamically located block that move, that float in memory. So you can never actually know at what given address your code is. It's a very difficult situation. So it's not a classic buffer overrun or code execution interception situation. So this is why you cannot actually rely on any Java object, dynamic object address. So this is a completely different situation, and some new approaches must be undertaken in this situation. Okay, so what I simply did, because I've told you that the garbage collector is running from time to time. It compacts the heap memory, so the memory layout changes. Since the memory layout changes, the Java bytecode locations also changes. Yeah? Methods location changes. If we are going to perform a reliable inter-method jump, we have to simply make sure that this inter-method jumps always results in jumping to the proper bytecode location. So how I simply avoided that, I just simply changed the method bytecode itself, just in order not to perform this inter-segment jump. Because when I was doing, for example, 20th or 50th intercode go to inter method go to jump, I was given a bytecode illegal bytecode exception, or I was given, for example, this was the exception I was usually given, or some other Java exception. The whole mechanism didn't work in a reliable way. This is why I simply changed the body of the exploitation method in such a way so it was just what I needed. Yeah. So I simply put this integer return instruction at the end of this method just for the purpose of having a body of a method in one place, in one solid block, not to perform the inter-method jumps. Yeah. So, but before I could do this, I had to break memory safety of Java. I had to do several go-to jumps. But this can be done in quite reliable way. So if it is properly implemented, the exploit code can actually will never trigger the garbage collection operation. So, okay, one more thing is that because of this garbage collector operation, it is advised to use the iReturn instructions or any instruction that operates not on object references but rather on integer items, just in case not to trigger the garbage collector operation. Because if you use some aReturn or the object references instructions, it is possible that garbage collection might try to do something with our reference, which isn't actually any valid object reference. And this could, for example, make the phone reset, reboot, etc. Oh, excuse me. To the table, oh here, okay. So what's the impact of the vulnerabilities that I presented you? I have just simply verified the CLDC10 specification and how many phone models follow this specification. This is a table that presents that there are many different phone vendors that have Java mobile devices with potentially vulnerable KVM version. I just want to indicate this potential word because actually I have just tested 2 or 3 phones, Nokia phones, and in some circumstances the phone might not be vulnerable. This especially considers the very new smartphones, for example Nokia 6600, because it, for example, contains completely different virtual machine. It's not KVM anymore, it's Monty VM, yeah, the new class of virtual machine with just-in-time compilation, etc. So it's up to the vendors to confirm that which devices are actually vulnerable. The list of the complete list of J2ME devices can be obtained from this address at some microsystems website. So I think that some estimations actually vary here. Next slide, next one please. Okay, thank you. Estimation actually vary here. Some say that there are 100 millions, some say that there are 350 millions of Java capable mobile phones. I don't actually know how many of them there are. Definitely there are lots of them, so the impact of the vulnerability is quite big. So we now know that there are the flaws in KVM, and this is just the beginning of doing something nasty on the phone. So first, in order to do something nasty, upon having a bytecode verifier flaw, it's good to break Java type safety. So as I said it already many times, Java is type-safe language, and in order to perform any type conversion operation between any Java data items, this must be done in a very implicit way. So you have to always use very specific instructions for converting between some primitive types or some complex types. So, and Java has support for that. And this, according to the Java language specification, this should be only possible to be done in such a way. However, it is possible to perform the so-called type confusion attack. And in this attack, we usually have a condition which is a result of some flaw, for example, in bytecode verifier. And in this condition, it is possible to perform some cast operations from one Java type to any other completely unrelated type, and can be done in such a way so Java type casting rules are simply violated. And the goal is to perform illegal cast in such a way so memory regions can be accessed, memory regions belonging to some other objects can be accessed in a way so that they were actually belonging to the object from which we were doing a cast. So here we have a short diagram of how what's all about the type confusion attack. In the first situation, we have a situation before type confusion attack. We want to reference a variable field from a given object instance. So we must issue proper getField instruction. This getField instruction contains proper field descriptor. And Java runtime, in order to obtain such a variable field from a given object instance, simply needs the pointer to the object instance, and it simply needs field descriptor. And upon having this information, Java runtime can decide whether a given field can be accessed. In this situation, this field cannot be accessed because it has a private access field modified. But after performing type confusion attack, for example, if we can perform illegal cast operation, and we can, for example, cast a reference to one object to, for example, a spoofed class, a reference from trusted class to spoofed class, the situation when it comes to referencing the variable field of the spoofed class looks like this. We again have a source object pointer, which is the pointer to our object instance, in this case the trusted class, and we have a field descriptor, which in our case is a spoofed class. So we see that virtual machine references the spoofed class, and if we have a spoofed class constructed in such a way so that the variable field has public access, this access will be allowed by the virtual machine itself. So by doing so, we can actually break the Java safety, Java safety, which should be guarded at the language level, at the level of private, public, and protected access field modifiers. So, unfortunately, in KVM, it's not so easy to be done, because in Java 2 second edition, type confusion is possible since there are no runtime checks when it comes to accessing different fields of classes, when it comes to issuing get field, put instructions. These attacks, type confusion attacks, are also possible in KVM, but they must be modified a bit in order to reflect the very specific environment that we have here. So what we have here that might make this attack a bit difficult. We have system classes in ROM and read-only memory, or flash. We have bytecodes which are interpreted. They are not compiled into native code. And one more thing that we have here is that fields and methods are looked up dynamically by a hash key computed from a field method descriptor. All of these things here makes it a bit difficult to perform classic type confusion attack that is known for years now with regard to the classic Java virtual machine. So I tried to adopt some new technique into breaking Java type safety in the KVM environment. So what I did, I simply copied the trusted class into RAM, so into the memory which is under my control. Yeah? So what I did also was I changed the object instance in such a way so it didn't reference the original class definition in ROM. It simply referenced the copy of my class, which has been especially prepared for the purpose of conducting this attack. And one more thing what I did, I simply changed the pointer to the field table from the definition of this copy of this class trusted in such a way so every field was simply set to public. On this example. So it's possible to perform classic type confusion attack also in the KVM environment. So what you have to do, it's very important to maintain this statement. So we always have to look up classes by the original field descriptors or method descriptors, because there is always a proper field lookup operation which is done internally by the virtual machine. And this field lookup operation, it simply computes a hash key upon which a given method or field is looked up. So we have to maintain this component when it comes to type confusion attack in the KVM environment. Because if you for example had spoofed class here, we would never be able to reference any field from the original trusted class, because lookupping the fields would always return null for spoofed field descriptors. Okay, so we know that there are the flaws. We know how to break type safety of Java language. Now let's try to break memory safety. This is the other step of attacking Java. Memory safety is all about obtaining unlimited read and write access to the native memory of the host device. So in the case of the type confusion attack, I verified that this can be done in at least two ways to break memory safety on my Nokia phone. I did it through a field variable. I also did it through the table of bytes. So the first method is here. What I simply did, I created a spoofed class with some integer value. Then I simply casted some integer value, where I was simply denoting some arbitrary memory addresses. I was simply casting this to the spoofed class. In the result, I was able to reference arbitrary memory addresses through the spoof object instance and its value field. Yeah? So I was simply moving. I was just trying to trick the virtual machine and so that it thought that the actual spoofed class instance was of different memory addresses. So this is how it worked. When it comes to the, thank you, when it comes to the other attack, breaking memory safety through the table of bytes, I simply created some table of bytes. I set some fake Java object instance header, which were denoting that this table of bytes, fake table of bytes, was 4 gigabytes long. Yeah. Then I was obtaining the base address of this new fake table, yeah, which was 12 bytes from the beginning of the original table, and then I was doing a cast to simply do the array of ints. Yeah, by doing the cast to the array of ints from properly set up fake table, I was able to trick here the virtual machine into thinking that it is dealing with a table of integers that has of the size of 4 gigabytes. Yeah, and here I could, having a 32-bit space, it's all about accessing a 4 gigabytes memory space. Yeah, so having a 4 gigabytes, the table long, which was long, of which size was 4 gigabytes, I was simply able to access the whole memory by giving proper indexes here. Yeah. So by giving such an index, I was able to reference any memory location at a given address. So this is how it worked. Oh. Sorry, again. I think that before. Oh, no, sorry, this one. So it was all about breaking memory safety when it comes to gaining read-write access to the memory of the host device, but it is also possible to actually run any native machine-level code on the device. So I also proved that. What I did, I simply properly set up the methods table of my class through which I wanted to jump into native code. What I did, I created simple dummy class. In this dummy class, I had two methods, the constructor and some jump methods. I set up the descriptor of the second jump method in such a way so virtual machine thought that this was a native method. So it thought that this was a native method. Invoking jump method from a dummy class was simply yielding in a code execution of a given code. So here I was pointing this code pointer to my table of ARM opcodes, and I was able to execute any native code on the host device. Okay. Oh, sorry. Okay, I think that I have, reliability issues. Okay, so every time when you do anything on the device that tightly interoperates with memory, you must always take into account the behavior of the garbage collection. So you might occur some reliability problems related with that. So it's not so easy actually to jump into a code location that is embedded in a given table of bytes allocated through the Java malloc operation, because in the long term, this location will not be valid because it will be moved to some other place by the garbage collection. So I verified that it's much better to, for example, use the native OS memory allocation routine for the purpose of obtaining stable memory region, which can be further used for example, callback, messages, handlers, etc. Can I ask you for? Okay. I also conducted the so-called class spoofing attack. In the class spoofing attack, the goal is to get access to some protected Java native methods of system classes. Yeah, system classes usually implement some protected, very special functionality of the phone. So it's sometimes very useful to just get access to this functionality and to call it freely. What I did, I simply created the instance of my dummy class with some dummy methods and public access. What's important here is that I had to use the same method name and descriptor in the spoofed class, in my dummy class, as in the system class. This is very important, and this is the result of the way the field lookup and method lookup operation is performed in runtime by KVM, and it is done by the hashed key. Yeah. So then, upon having such a dummy class, which was actually the mirror of the system class that I wanted to spoof, I simply put the pointer. I didn't do that. No. So I simply put then the pointer to the method table from the spoofed class to my dummy class. Yeah. Then I was simply invoking a given method as if I was invoking a method of a trusted class which I was spoofing. So this was quite simple and quite obvious. And what I also verified is that class spoofing worked very well for protected fields from system classes, but also worked very well when it comes to methods from system classes. I was able to spoof both Java methods as well as native methods. So, for example, I was changing the definition of the system methods from Java lang package, and this was getProperty method. It was used in some very specific situation. I needed this functionality to be a bit changed. So spoofing system classes turn out to be very useful in the case where I wanted to execute system methods and when I wanted to change the execution of the system methods. For example, some security checks or user dialogues are usually invoked from within system classes. So if you had the possibility to change the behavior of system classes, this is very needed functionality to spoof these classes. So now this is the first part. In the first part, I tried to give you the overall look at the KVM vulnerabilities that I actually detected and the way how these vulnerabilities can be actually used to break Java type safety in the first place and then break memory safety in the second place. So this is just the actual beginning of doing something, of trying to do something messy in the phone. And from this point, I spent a couple of months actually to reverse engineer this phone. This is my phone that I use every day. So it was really difficult. Yeah, I have to admit that this was really difficult. And what I should mention and indicate here once again, the whole thing with these KVM flows is not so reproducible. It's not reproducible so easily. This is not an easy way. Yeah. So coming back to the reverse engineering process, this is the Nokia phone I was reverse engineering, in which I was spent a couple of last months with. So what's important here is that this is the so-called closed DCT4 phone. This simply means that the flash files of the phone software are not available in any form anywhere. At least I don't know any place where they can be available because these flash files are always encrypted. The second way is that no way of executing any user code has been ever thought to be possible at this device. Yeah, it was always thought as a closed device. Yeah, a device providing a given functionality, and the only way to execute anything on it was through Java. Yeah, not native code. So, but here we have a type confusion situation, we have memory safety broken, so we can actually access any memory on this device. We can actually execute any native code on this device. So what I used it for and where it actually brought me to. Oh. Task definition, please. Task definition. Oh, here, okay. So I just tried to approach this as I usually approach any math problem. So I had task definition. I wanted to actually find out what is actually possible to do from within some untrusted middle application exploiting one of the bytecode verifier flows in the environment of this Nokia phone. At the input of this task, I had a midlet which was escaping the KVM sandbox and which was breaking memory safety. So I had some class which was which I could reliably use to read, write memory, as well as to execute any ARM code on a device. Oh, can I ask you to? Okay, so In the first step, what I was doing, first I tried to pick and poke in memory. So picking and poking memory of native device usually reveals lots of information about the software of this device. So you can, for example, obtain information about the visible address space. This is one of the most interesting things here. Yeah, you can, for example, locate some C strings in a phone software. Those which are special interest here usually begin with Java or some com prefix, which means that these are the classes implemented by a given vendor. So you can see some of the strings that I was able to detect by picking and poking memory. Here you have I was also able, by picking and poking in device memory, I was also able to obtain some more detailed information about the actual representation of Java objects in memory. This is very important. If you want to try to do some nasty things with Java, you must be aware of some of the representation or all of the way KVM operates. I was able to obtain information about object instance representation, garbage collector header, class structure, method table, field table, and all of that was done through some trial and error approach. I simply was testing different class definitions with different access, different number of fields, etc. So it was reverse engineered through this. Again, what I tried to do, I was able to peek into memory, but it actually gives you nothing because you can read memory, but you cannot do anything on the phone. So I tried to disassemble Java bytecode methods. And by doing so, I was able to find more detailed information about what they were actually doing. There are lots of native methods implemented on the phone, which do lots of very interesting stuff. Why this is profitable, actually? This is profitable because sorry, I'm talking about native methods, this is bytecode methods. And when it comes to bytecode methods, it's profitable to disassemble bytecode methods. It's profitable because Java is a type-safe language, and any bytecode must be accompanied by lots of type information. Yeah? So any reference to the field or method must be associated with such a type information. And this simply gives you information about what a given bytecode method does. Yeah? So it's very profitable. And when it comes to native code, it's very profitable to disassemble native code because some J2ME core system classes interoperate with the native operating system very closely. Yeah? They usually invoke some of the host operating system functionality. Yeah? So it's very profitable. It's good to start to actually reverse engineer some J2ME core system classes because you have their declarations in the specification. You know what methods they are exposed to the application programmer, etc. And upon having the knowledge about this, application interface of some J2ME methods, you are able to find out, for example, how KVM actually passes arguments from Java to native methods. So it's very profitable. You can also find out some information where the internal bytecode interpretation routine is actually located by simply looking at the ARM processor link register, yeah? Because there is a return address always saved in it. So by disassembling native code, I was also able to identify how methods and fields and method field tables were looked up. Yeah, I've mentioned that they were looked up by using they were looked up dynamically by using a hash key. So I simply, by reverse engineering Java language package, the class and its 4 name methods, I was able to find more about this process. I was also able to build databases. I actually was building a database of some noun subroutines upon disassembling code. If you meet some subroutine for the second, third time, it's completely useless to again find out what it's doing if you have already done it. So if I for example, reverse engineered a given subroutine, I was giving it a name, and this name was descriptive enough, so I didn't look at it again when I spotted it in the code. So by disassembling, I was also able to find out lots of information about the internal KVM operation, because as I said, it was usually invoking some very specific functionality related to the operating system itself, the operating system that was running on my Nokia phone. So, however, it was not enough. Yeah? I wouldn't gain anything by simply poking into memory. I wouldn't come to any results by just poking into memory or disassembling code. This is tiring process. It takes lots of time, etc. So maybe skip this slide. I started to search native code. Yeah, because the native code subroutines have hundreds of instructions. They sometimes have thousands of instructions. How are you able to actually disassemble it, having a 4-line display, yeah, and no knowledge about the operating system itself? Yeah, so I started searching native methods. I started searching for some specific code patterns, and this included references to some global variables. This included some methods invocations or some debug strings, because there are lots of debug information left in the case, for example, of my Nokia phone. So you have some debug strings that actually describe you what's going to happen next. Yeah. For example, we are going to unload applet, or we are going to send some message to some process. Yeah. These strings are in the memory, and they can be easily spotted. So upon gathering all of this knowledge about subroutines, global variables, this usually helped me identify what a given subroutine was doing, yeah, by simply searching for some global variables or some method invocations. So, but as I said, it was completely, very tiring process, and it wouldn't actually, I think it wouldn't bring me to any interesting results. So I started to emulate native code. So I wrote a midlet, which was actually emulating the ARM microprocessor. So my midlet, which helped me a lot, was doing one of these things. It simply executed ARM microprocessor instructions working in fun mode. I was emulating all of the instructions from the ARM fun mode. This included stack operation. Yeah? I was able to emulate the execution of conditional branch instructions automatically. So when I was just going down through the 4-line display through the code, when I was at some location that was doing a conditional jump, I was also able to automatically take the branch as if it was taken by the processor. Yeah, because the decision was computed upon the current state of the conditional flags. Yeah, I was able to do this automatically. So next, we have emulation slide 2, I think. Emulation step. Okay, sorry, 2 slides. Next, okay. So I was emulating the contents of ARM registers, stack and memory in such a way so this contents was automatically tracked. Yeah, I didn't do this. Okay, I was naming the contents of registers and stack appropriately. So when I was looking at the register view, I simply knew that a given register contains a value from the stack because it was prefixed with a proper ST keyword. Yeah. I implemented step in, step over, and run to functionality because you have some call, you have reverse engineered some call. It just took you a day or two. It contained 100 or 1,000 of instructions. So you don't want to again go through 100 or 1,000 of instructions in a single way. So I implemented a step over functionality. So I could just give my midlet information about to which point in the program he should emulate execution of the native method. So, and what's the most important thing here is all memory accesses that I implemented in my midlet, they have been virtualized. This simply means that I had a cache of all write operations. Yeah, I wasn't actually writing to the native memory because what you will find out later in this presentation, native memory in Nokia OS is globally shared. I didn't actually want to in some way interfere with the whole operating system. Yeah? So I was using the cache of writes, and I was referencing this written memory cache whenever I was obtaining, when I was accessing the memory. So The other thing why I implemented this, I was actually afraid to break my phone. Yeah? I didn't want to break my phone and be unable to finish this work. Yeah? So this is why I implemented the virtualized memory cache. Oh, okay. So what I did next, just step 5. Okay, here. Okay, so while doing all the disassembly emulation work, I was constantly maintaining the database of non-subroutines. Whenever I was able to reverse engineer a given subroutine, finally, I was giving it a name, so whenever I spotted it again in the code, I was able to see a branch invocation of a given name, not a branch invocation of a given address. I also implemented my emulation method in such a way so I was able to change between different views, and this changing of views was done upon proper context. For example, I was able to automatically check what a given memory location, what value a given memory location was containing upon simply pressing the left arrow key on the instruction which was referencing a given memory location. I was simply able to move from the register view to memory view if a given register was containing memory reference. So this was quite context-aware mid-led, so I could quite fast move around different views, and it was very, very helpful for me. So as I said, it would be quite difficult, if not impossible, to finish this work if I didn't emulate native code. So there were, however, many obstacles that I had to fight. The first one was that Nokia 6310i has very painful size limit when it comes to the mid-led archive. It has just 32 kilobytes. I had to rewrite my emulation mid-led 3 times to just fit that limit. Yeah. So the second thing is that the phone offers about 160 kilobytes of RAM for mid-led applications, dynamic RAM. I also had to fight this because I was maintaining the cache of write operations. Yeah. During the invocation of a given native method, there might be, hundreds of write operations. You have to maintain information about all of this in your cache. So I had to fight this as well. So, and last, it was, as I said, it was quite difficult, to do all of this analysis on a 5 lines long display. So what I did in the next step, I tried to speed up my work. So I tried to locate subroutines that were establishing some communication over wire with a PC. So by doing so, I was able to do the whole emulation work off device, yeah, on a PC, which has, unlimited amount of memory, CPU power, etc. Yeah. So I use a client server architecture, debugging architecture. So I had a debug agent midlet that was running on device. It was primarily responsible for reading, writing device memory upon request received over wire from a PC. And PC was able to keep track of all the changes, memory writes, etc., the whole call tree that was involved in memory, because the emulation was done on a PC and it had lots of memory which could be fit with that information, and I had no limits with regard to that. So this is how I speed up my work. Okay, can you just please me? Okay, so I will present you the two midlets just in the slides, which I used for the purpose of the reverse engineering process. I had a couple of them, but these two, I think these two were the most useful for me. The first midlet simply allows me to dump a method list for a given class. Yeah. So if, for example, it looks like this. You have a main application view. Here you put the name of the class, and then you're able to browse through its methods. So this simply allowed me to locate some unpublished native methods implemented by, for example, Nokia or Sam. And it's not shown here on the slide. I was also able, upon locating some native methods, I was also able to see its address here, and I was also able to, by pressing the right key, to disassembly its definition and to simply go through its disassembly. The next midlet, the emulator midlet, looked like this. So you see 4-line display, yeah, several views. Here you have a disassembly view. This bar shows the current location of the emulation process. You see the current location where I was emulating. This shows the registers view. You can see that registers and their values are named appropriately. So, for example, link register here is named in such a way so it denotes that the value it contains is a return address. Yeah. So what can we see here more? I could see the whole call stack view. Yeah. Just for the purpose of locating where I am or how deep I am. Sometimes this call stack was 11 to 15 of depth. Yeah, that depth level. So some native methods are really complicated. Yeah, to reverse engineer. I was also able to disassemble memory view. Yeah. So this is the last memory view. So this is the emulator midlet. So, and this was the brief introduction to the process that I took when it came to reverse engineering the phone, KVM and the phone. Yeah? And now I will present you, on the next couple of slides, I will present you what I actually was able to find out about the Nokia OS, about the key. Nokia OS, primarily about Nokia OS. So I found out that it runs on ARM microprocessor atop of some embedded RTOS operating system, real-time operating system. I'm not giving you the name of this operating system because I actually didn't find any details with regard to this. I have some hints. I think that I know who is the vendor of this operating system, but I don't want to go into this because I might be wrong and it's unnecessary to say something that is wrong. So I find out that there are about 56 tasks, 38 in hexadecimal, which share the same global memory space. Yeah, this includes RAM memory as well as flash memory. I found out that it's possible to communicate with the tasks communicate with each other with the use of the so-called message passing inter-process communication mechanism. I found out that my Java task in which my midlet was running has a task number 36 in hexadecimal, and that it was running at the user level of the ARM microprocessor. And that it was implemented as one native thread. Why one native thread? Because when I executed the ARM code, which was simply an endless loop, it frees my phone. Yeah, this simply means that this was one native thread. And again, input-output peripherals are handled as memory mapped devices, which are also globally visible on my Nokia phone. So next, I found out that structures describing Nokia's tasks, this includes task name, flags, starting address, message handler, message queue, they occupy dedicated memory slots. And they are the same for a given software version. This is also the case for some global variables, which are always located at the same memory addresses for a given software version. What's dangerous here is that Nokia phone models software implements some potentially dangerous methods, which is Java located in Java language package system class, and by issuing a get property call with micro addition platform stream, we are able to obtain very detailed information about software version of a given Nokia phone and its name. Yeah, it's very dangerous when it comes to, for example, approaching some attacks that are that can be performed on a wider set of devices. Again, what I was able, this is just a brief memory map that I was able to locate. At the beginning, there are of course interrupt vectors. I wasn't able to access them. I was running on user level, not the system level of the microprocessor. So I wasn't able to access them. So I didn't actually find out the interrupt vector addresses. Then you can see that there is some RAM memory, there is some flash memory. So memory map, which this is memory map for this model. I am not sure it reflects any other Nokia model. What I was also able to find out the list of the tasks that were running on the phone. This is the list of these tasks, and you can see that some of the names might be quite. Some of the names might reveal what a given task actually does, for example, GPRS related tasks, Java task, OS idle task, but some of the names are, for me, as for now, completely unknown. Yeah. So then I was also able to locate the so-called objects directory. When I was reversing the record store class, I just wanted to find out how it is possible for a Java application to use the persistent storage of data, yeah, that doesn't that that is maintained across powering of the phone. So I started to reversing the record store class, which is responsible according to MITP specification for doing this. And I found out that actually it didn't contain any native methods, but it was referencing record store file class. So I started reverse engineering record store file class. And then I found out that it contained lots of native methods. Yeah? So I started disassembling, emulating, and I took all the approach presented before to find out how actually this persistent record storage is implemented on my Nokia phone. So I actually find out the way how file system objects were implemented on the phone. This included files and directories, but I also find out how some more information about it. Specifically, I discovered the mechanism that was used for storing some other information in the phone, and that included, for example, phone book, SMS messages, audio records, WAIP cache, dialed numbers. Yeah, because all of the information on the Nokia phone is kept in the so-called, I called it a root directory. Yeah, objects are referenced by object ID and by object type. In this example, object type 9D in hexadecimal. This is simply the directory entry. Yeah. So in a root directory, there are items which simply describe the chains of objects of a given type that are maintained in the phone's permanent memory. So I don't want to go into details when it comes to this slide. In general, you have one directory of different object types, and you can look up lots of very interesting information when it comes to the user data or phone configuration from this directory. So this is how the file system killer looked on my phone. These are object IDs, they are names. These are all object IDs of the type 9D, which means directory entries. So you can see just directories contain application, etc. So I was also able to actually reverse engineer inter-process communication that was taken on the phone between different phone tasks. So I reverse engineered the socket protocol class, and what I was able to find out, I found out that the socket class was, and it's specific in its open zero method, was sending a message to some other task, the fboost task. So by doing so, it really helped me a lot by finding out about the inter-process communication, and not only this class. This was just the beginning. There are also some other class, device control, for example. But it really helped me a lot in locating this and more information about this mechanism. So when it comes to messages sent between tasks, you can see here that every message has its message ID. Every message has its length. Every message has its destination task ID, source task ID, and every message holds a given data. So, sorry. So I think, where are we? More. Of course. And that was sending these messages received from some other processes over wire to my PC. Yeah, and I did it. And it was possible just because Midas application has access to the RAM memory. And it was also possible because this RAM memory was globally shared among Nokia native processes. So by doing so, I simply obtained lots of new information about the way Nokia processes interoperate and the way how they communicate upon which events trigger what kind of communication, etc. So, yes?
Sorry. How are IPC calls authenticated, or are they not authenticated at all?
I would say they are not authenticated. I haven't verified that so deeply because this message passing application I wrote it about 2 weeks, week and a half ago, 2 weeks ago, and what I found out is that it is possible to replay messages. So if it's possible to replay messages, you can just start thinking whether there is any authentication. Yeah, even if there is any authentication, so it's weak because messages can be simply replayed. Yeah. So I gained lots of information about the whole interprocessor communication on my Nokia phone. So what actually was possible also when it comes to interprocessor communication? I simply installed a resident code on my phone. Yeah, and this resident it's possible to from within this resident process intercept communication that was occurring between native Nokia's processes. I simply was intercepting proper message handler. For example, I noted that there are tasks that constantly send messages to some other tasks. This includes GSM networking, for example. And I use native malloc, not the Java malloc operation for storing my code of the handler, message handler. Yeah. Okay. When it comes to interprocessor communication, for sure I am able to intercept communication occurring to these processes. Yeah. But I was also able to intercept communication that was between SMS server and other tasks. Yeah. Can I ask you to just? Okay. So the next step when it came to reverse engineer the phone was to try to do something to verify whether it is possible to write the flash memory from within the phone. Obviously, it was according to my intuition, it should be possible to be done because Java applications can store data in a persistent way. So I started reverse engineering the record store class, and I knew that I found out that the actual writing of the flash memory wasn't done from the record store class. I found out that it was done from the midlet manager class, yeah, and it's exit internal method. So actually, the flash writing of the midlet data was done at the application exit. It was very tricky to spot actually for me. So I had to go through all the record store methods just to find out at the end that it's useless for my purpose. Yeah, here. So during the midlet operation, all the buffers are cached in RAM, and only at the time of the application exit, they are flushed with the use of the internal RMS flush buffer subroutine to the permanent memory. So when it comes to flash memory, I actually was able to locate some objects in RAM that contain information about some, they contain, for example, flash-based address and address it to several subroutines that could be issued to simply flash controller. So there is a subroutine to program command, there is a subroutine to sector erase, erase suspend, etc. commands. You can use them, yeah, from within your Java application. I was also able to directly flash the memory of my phone. I verified that on my Nokia phone. It is possible to simply issue some write operations directed to specific I/O ports in some specific order and some specific cycles. So I was able to write flash on my phone. And what's important here is that flashing can be done usually in such a way so bits 1 can be changed to 0, but not in the other way. In order to change 0 to 1, you have usually to reprogram the whole flash sector, and I mean to erase it. So when it comes to malicious midlets, I wrote a couple of them. First, I wrote a stealing data midlet. What this midlet was doing, it was simply accessing the object directory of my Nokia phone. It was accessing the SMS messages and phone book directory entries, and it was simply sending this information without user knowledge or asking the knowledge for the permission to some arbitrary internet address. I verified this. This works very well on my phone. So, okay. Okay, here. Okay. As I said, I was able to connect to the internet without, the user knowledge. Normally, when you establish HTTP connection object, when you create the HTTP connection object and connect to the internet, there is a a system dialog that appears in the phone and asks the user, do you want me to connect to the internet? Do you allow for such operation? I was able to bypass this whole security mechanism simply by changing the way directory objects were visible for the operating system on my Nokia phone. Yeah, since lots of information is referenced from RAM. Yeah, I simply changed RAM in such a way so that the process doing this security dialog thought that my mid-level application is trusted. What I simply did, I simply changed the Java application descriptor file directory entry in permanent memory in such a way so that it contained proper internet mid-level access level. Yeah, I used for that purpose the record store class because I wanted to write to Flash. I used the RMS Flash buffers routine because I wanted to have the changes to be visible immediately. Yeah, not after the second run of the midlet. Yeah, this was the first version of this midlet. So, can I ask you to just, okay, thank you. And I changed the object directory in RAM, then I established HTTP connection to the internet, and by doing so, there was no warning dialog presented to the user, so I was able to connect to the internet freely without, by bypassing any security measures. So then I restored original structure of the objects directory in RAM because I was a little bit afraid whether this might influence my flash memory a bit. I changed some cache in RAM. I didn't know how it actually is, whether it is actually taken into account when it comes to phone switching off, etc. So the next midlet which I implemented was the one which was changing the phone permanent memory. And I think this is one of the most dangerous operations that can be actually done from within the untrusted midlet. Because if you can change the permanent memory of the phone, you can actually change the phone software and potentially install some backdoor. This is possible. I haven't verified that. I didn't want to have a situation where my phone doesn't stand up, doesn't work. Yeah. I didn't change that. I think that there might be some checksums in the phone software that protect against this. It's not so easy, but I think that it's possible. And it is also possible to make the phone unusable by erasing the whole flash memory. I know that, I think, I shouldn't say no. I've read from the documentation of the flash controller that's used on my Nokia phone that it's possible to issue 6 writes to proper addresses, and this 6 writes simply issue the whole chip erase command. Chip erase command simply erases the whole flash memory. 6 writes. Yeah? Okay, again, I also verified that it's possible to send SMS messages from my phone without any user knowledge. So what I simply did, by intercepting the communication taking place between different tasks on my mobile phone, I was able to sniff the whole communication. When I started to sniff the communication, the messages that were sent to SMS server, I just found out which message is responsible for the command send SMS message. So I found out that this is message ID 0202 in a hex, and that it is sent to MDI send task. So what I simply did, I just grabbed this message, replayed it. This is why I was talking about replaying. I replayed it. Actually, the message was sent. Yeah. No, nothing was presented to the user on the phone that the actual action was taken from the untrusted middle. Okay, and the last thing I think I want to mention is that the whole interfering with the interprocessor communication is also very dangerous because it allows to block or change some messages sent by given task in response to user actions. For example, think about an SMS sniffing application. For example, you install a resident application on the phone that intercepts messages sent to the SMS server. And for example, these messages are sent to the legitimate phone number, but they can be as well sent to some attacker's number. Yeah, this is possible. Yeah. I haven't verified that. I think that it's highly probable that some arbitrary phone calls can be also established through IPC. I was tracing some GSM call server communication a week ago, and I found out that when I was trying to establish a phone call, yeah, lots of messages were going on through my display. Yeah, I don't actually know what these messages mean, but I think that some further investigation might prove that establishing phone calls, GSM phone calls, can be also possible here. Okay, when it comes to future threats, I'm sorry that I am past the time. When it comes to future threats, I think that since there are more users of mobile devices now, I think that there are more of them. And this platform, the mobile platform, makes it very attractive for attackers and worm writers. So, in my opinion, we should expect remote vulnerabilities for mobile devices within the next 6 months. Yeah? I think it's very highly possible. Yeah? What's important in this whole KVM thing, in this mobile Java thing, is that actually vendors and antivirus vendors are not prepared for this kind of threats. Yeah? They are not prepared for remote vulnerabilities. Yeah? Because how are you able to protect users of the so-called closed phones? How are you able to install any antivirus or protection mechanism on their phones? This technology is not protected for these kinds of threats, in my opinion. And what's more important, since I believe that one of the platforms that are the most risk are Palm OS, Symbian OS, and Windows CE. In this presentation, I simply focus on the closed Nokia phone because for me it was the bigger technological challenge to break this phone, not the open phone when you have debuggers. You can grab your hands on every binary that is on the phone, etc. So I think that these platforms are the most risk just because they are open. Yeah? Okay, and finally, I would like to indicate that all of the KVM attacks and methodologies that I present in this presentation, all of the malicious method examples, I verified all of this stuff in practice. Yeah? So on my Nokia 6310 iPhone. So it doesn't necessarily might reflect other phones. You should always take it into account. My Nokia phone, yes, but not necessarily other phones. Some other phones may be running on some other very specific operating systems, RTOSes or embedded systems. I intentionally removed detailed information from this presentation about addresses of native methods, system calls, global variables, etc. The same considers the way in which to interoperate with the phone. It took me 4 months to find out about this. And I intentionally removed it because my goal is not to give people the tool to reproduce it easily. My goal is to increase the awareness of the threats, yeah, and to indicate that threats like this are possible, and to bring maybe to start thinking about some technological changes when it comes to closed phones or the whole mobile technology, because we should be prepared for the remote vulnerabilities. My opinion, this is a 6 months period. So also plan to release a research paper with all the details, including some additional material that actually didn't fit into this presentation. I think it should last about 3-4 hours. This is how much information I actually acquired. If I would like to be very detailed, 3-4 hours easily, 3-4 hours. So I think that I will read this paper at proper time, but not earlier than a couple of months. Okay, that would be all for now. Some of the valuable resources that you may want to look at. These are the resources that are a must to read in order to understand all of this stuff. These are the resources that I actually read many times. Yeah. So, thank you for your attention. Sorry for